And then there's swings. This is the accelerator at Six Flags. There's no pumping your legs on this ride. In fact, they haul you back and up 160 feet and then let you go. Up on the top of the tower, you have a lot of gravitational potential energy, or GPE. That GPE gets transferred when you drop very quickly into kinetic energy, or KE. This energy transfer is the huge kick in the pants. Now, if air resistance were negligible, these flyers would return to the point at which they were first dropped. But air resistance is a problem. Energy is sucked out of the system by a non-conservative force and cannot be returned to the system. And therefore, they won't go as high or back to their starting point. Now, I want you to watch the flyers where they start, and then on the return swing, how high they go relative to their starting point. Right now, their gravitational potential energy is going up, 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 and up. GPE is energy by virtue of location. As they near the top, their gravitational potential energy will be as much as they can possibly have. Now they're at the top. As soon as they let go, all this energy is going to be transferred into kinetic energy. Here they come. Now check it out. They're going to fly right over us. Now watch as they go back. Watch where they come to relative to where they started. Right there. The difference between where they started and where they returned on their swing, that vertical distance is equal to the amount of energy sucked out of the system by air resistance. We have spent a tremendous amount of time talking about work and the fact that work is a transfer of energy. Well, we've also been focusing really on the forces that act conservatively. Now, a conservative force is defined as a force that transfers as much energy between 2 points going one direction as it does out of the system going between those 2 points along any other path. And from that expression, we have developed a sense of what we call the conservation of energy. And this is our starting point. The conservation of energy. Well, this statement holds true for only conservative forces in action. And if we were to add this term to the other side, we would end up with the expression of Ke plus any change in potential energy equals 0. Now, we have defined the sum of all energy in motion and all energy being stored as the total energy of the system. Now, when only conservative forces are acting, we are saying that the total energy in the system equals 0 or remains constant. That's what this is. That's what this expression tells us. It tells us that when only conservative forces act, the total energy in the system remains constant. That's what conservative forces do. They neither transfer energy into the system or out of the system. It just transfers energy from energy of motion to stored energy and back again. Well, what if the total energy in the system, represented as change in Ke plus a change in potential energy, did not equal 0? What if the sum of all kinetic and potential energies in the system didn't equal 0, which is to say it didn't remain constant? What if the total energy in the system didn't remain constant? Well, what we're saying then is that energy must be being transferred either into or out of the system. That's what we're saying if we make the statement that the sum of all the energies does not remain constant. We're saying that something else has to be putting energy into the system or taking it out. Because if those forces weren't there, then the energy would remain constant, and that's a reflection of conservative forces acting. Well, in this case right here, the only way that this can happen, the only way that you can have the sum of all the energies not equal to zero is if there are non-conservative forces acting. And so our next statement is that the total energy plus the total energy of motion and stored energy, it doesn't equal zero, but it must be a reflection of a non-conservative force at work. We're saying that it doesn't equal zero, and therefore any energy that's remaining, or what the value of this difference is, must be representative of the total energy transferred due to a non-conservative force. Well, we end up with this as our expression. Change in kinetic energy plus our change in potential energy. From here on out, it's simply an expansion. So let's identify all of our expansion quantities, and we have two as potential energy that experience changes in potential energy and kinetic energy. So let's figure out what it means and how to determine the work done by a non-conservative force.